Science dominates every corner of our modern world. Its influence is ubiquitous. From the iPad and the plasma screens in our homes, to the Curiosity rover trundling across the surface of Mars, beaming back high-resolution images of its terrain, and the Large Hadron Collider, smashing particles together at unfathomable speeds, searching for the fundamental building blocks of the universe. It is no wonder, given its track record and the sheer boldness of its ambition, that science is placed on something of a pedestal in our society, and that the rudimentary assumptions on which it is based go largely unquestioned. Philosopher Jim Schofield attests that there are fundamental flaws at the very heart of the scientific method, that while allowing for huge technological developments, actually hinders our understanding of the natural world around us.
So, Jim, before you started work on the philosophy of science, you were a physicist, a mathematician, and you worked in computer research with leading mathematicians. When and why did you begin to question this methodology?
Well, when I was very young, really, I went to university aged 18 and almost immediately found myself at odds with my lecturers in physics, who informed me of this particle called a neutrino, which was massless, chargeless, and yet vital to their whole theory. I was unimpressed and said so, but it didn't get me anywhere. But right from that point onwards, I was always questioning some of the arbitrary things that seemed to crop up, that seemed to be inventions rather than discoveries. And then somewhat later, when I was teaching maths, I was teaching calculus, and my students found it very hard to understand the calculus. I brought up the philosopher Zeno, the Greek philosopher, who had noticed that two assumptions that were at the basis of all rational thought by mankind, the ones of discreteness and continuity, were both inadequate in certain situations. But nevertheless, in spite of his paradoxes, which seemed unanswerable by the normal way of thinking of his colleagues, he was never taken seriously. He was considered to be a spoiler. But once again, I had to agree with him. So those were the bases of my being critical of the received wisdom.
And yet you worked in maths and computing and things for a long time, so you do have a deep understanding of the methodology which you criticise.
Yeah, it's not so much the subjects that I'm criticising, but I think the philosophical standpoint of many of the people who participated in it. I mean, I consider myself to be an able mathematician, and I've done quite a lot of research, but I don't take the standpoint of either mathematicians in general or physicists in general. I have a very different philosophical standpoint to it.
Something you talk about a lot in your work is this concept of plurality. How would you describe this idea, and why do you consider it to be part of the problem with science?
Well, it's kind of fundamental principle of pretty well all science. And in trying to understand reality, mankind wanted to try and pull out of the complexity of reality various bits that he could study. And it was quite difficult to do in the main. But there were a couple of areas where they could do it. One was the heavens, which seemed to be very constant and therefore interpretable. But this principle that they assumed was that if you managed to extract something from reality, what you had in your hands was what existed in reality. In other words, that anything that you extracted out was separable from its contents. That is the principle of plurality, and it's wrong. You can't do that. In my opinion, everything is determined by its contents. Everything affects everything else.
So to illustrate that, here we have three different situations under close study. Could you talk us through the process of how the scientific method is used to extract relations from these three examples?
Well, of course, these are very idealised cases. Yeah. But if you look at them, you'll notice that there are various things inside the three circles marked by different symbols, and they represent perhaps different processes. Processes that can be independent or could relate to one another, oppose or be supportive of other processes. But if you look at the three, they're all different. You will consider those to be three different situations. And in cases like these, it would be difficult to extract anything that you could use. So mankind, if we look on to the second picture, attempted to simplify those situations, all three of them, all different ones, towards some sort of way in which we could extract perhaps the most important things that were going on. So that's the second diagram. Now, taken to the limit, taken to their ideal case, we have the third diagram where all three only have one set of things remaining. They're typified by a plus and a zero sign. But they're relations that relate to one another, and we can perhaps extract a relation, in fact a numerical relation, we can get data from it, and then we have in our hands a law. Now, modern physicists would say that the law exists in all those three cases at the bottom. Therefore it's independent of those cases, therefore it's separable from any context in which it occurs, including the three at the top. That is not true. In the three at the top, because of the effects of other things, they're different in each case. So this is an example of showing you where separability can lead you astray. They were convinced, having got the same relation out of the bottom three, that it was a universal thing that they had found. It wasn't.
So this is one of the main mistakes.
I think it's absolutely crucial.
The assumption, the pluralistic assumption that scientists make about reality is that it's always separable into constituent parts, and those parts act independently. That's the key.
That's the idea.
So you advocate that scientists are making a mistake here, that it isn't a legitimate undertaking to separate those parts and use them independently. Why doesn't this work? Why should we be worried about it?
Well, of course, the first one is that it's not true, but there is a second one which is quite important, and that is that once they have one of these formal relationships, they think that the form alone is sufficient to tell you all you need to know about the situation, and that is also untrue. A form is an abstract thing. It's a description, and it's abstract. It's not sufficient.
Well, how have scientists managed to convince themselves that reality can be broken up in this way? How have they convinced themselves that form is the essence of reality, when arguably that is just an illusion?
Right, well, the animation was attempted to give you some idea, but the crucial word to bring into this is that they formed the world. They took a locality and they modified it until it was absolutely perfect for extracting relations from, or perhaps only a single relation from. They tailored what we call domains to display relations and allow their extraction. Now they learned to do this quite well, and they did it in thousands and thousands of cases. And this gave them the confidence to think that they were on the right track. They had found a methodology that worked.
So, if that is the pluralistic way of looking at the world, and that is the way the vast majority of scientists look at the world, you would consider your view different in that it's holist. Now, the word holist to most people seems to be tied up with alternative medicine or pseudoscience or something. Now, obviously, this isn't what the word holism means to real philosophers. So, what does it mean to you when you talk about a holistic approach to science?
Well, the first thing to say is it's the opposite of pluralist. What it says is that everything affects everything else. Nothing can be taken separately. Everything changes everything else that's there with it at the same time. Now, there's an experiment that was done many years ago, I think 50 years ago, by Stanley Miller. It's famous, it's called Miller's experiment. And he tried to see how life could possibly have arisen from non-living substances. And he set up this experiment with all the necessary gases and water and so on. that he knew to be there in the primitive Earth. And he just set it in motion with heat and a few other things to make it as real as possible. But it was totally sealed. And after a week, he looked into it and it contained amino acids, the building blocks of life. That is a holistic experiment of the first order. Stanley Miller's experiment.
Another problem that you see with science, as it stands, is its inability to deal with real qualitative change. There's some crossover here with what we've been talking about plurality. But there's something new. You say that change is assumed to be incremental by many scientists, whereas it can in fact happen very, very suddenly indeed. How do you explain this process?
Well, that's a big question.
Yeah.
It's a very big question, but it's an important one, you're quite right. The first thing to say is that this plurality attitude, it breeds the conception that all changes are incremental. That is, there's no really big things happening. They're either very small, tiny changes, or they're caused by random damage. And that's all that makes things change. And then out of the blue, if you're looking at the real world rather than some farmed version of it, a major revolution will happen, a big change, which doesn't seem to be explicable at all. Now, these turn out to be the key things that happen, because though stability is the rule and lasts a long time, the real qualitative changes that happen in the world happen in these sudden dramatic events, which we call emergences.
A lot of your work recently has been to do with the study of these emergences. We've got a graphic here. We've plotted data on a graph from some period of development, and at first glimpse it does look incremental. It looks like it's a gradual change over time. Explain to us what's happening.
Well, the first thing to say about this set of points is that they're fairly widely spaced at quite infrequent intervals. And when you take data like that, you don't see everything. So what we're saying here, this looks as though it's a nice relationship in a straight line, but let's have a look at part of it, blow it up to a bigger size and see if we're correct. So picture 2 shows the amplified portion. When we look at this, you'll see there's a discontinuity. It isn't a straight line. There are, in fact, changes that are not part of a smooth curve. The next picture, which is a further amplification, actually makes it clear that what's happening is a step change. That's inexplicable in most terms, so we have to go deeper in still. And when we do, we find that at the step change, there's a swoop downwards immediately before the step upwards. Further investigation shows what the form of this swoop downwards is. It seems to slip down as if it's going to infinity, and then it swoops up again until it makes the new level. The final picture is the one that's where we've got to in our analysis of an emergence. And you'll see that the actual swoop downwards takes place in oscillations until it reaches a nadir of dissolution, and then goes upwards in a creative way in another series of oscillations until it reaches a new level.
So what we're seeing is a sudden emergent event, a sudden change, which is hidden in the records, which at first seems incremental, but on closer examination you see that these sudden changes occur. Are these things hidden in data? Will we find them, or do you think they're too sudden, too quick to find in, say, for example, the fossil record? Are these changes?
I agree. I think they're too fast in most cases. It's the difference between the time of a period of stability and the very small time of one of these big changes is so vast that they're just invisible in most records. But there is a place where the record is good enough to deliver more information, and that's in a social revolution, which can take place over days, weeks, and even months, and therefore we can analyse it.
Obviously, things that take days, weeks, or even months really don't appear in fossil records or ice cores or anything else.
No, not at all. They've vanished.
And so the assumption made by scientists when they're examining those records is that the change has been incremental.
That's right. That's their first obvious conclusion.
Science, up until this point, using the things we've discussed, plurality, the assumption of incremental change, incremental evolution, has preoccupied itself with gathering data using those methods. And arguably, science has rooted itself in empirical data, in quantifying the world, in an attempt to avoid ambiguity, to ground itself in something which is hard to question from the outside. When faced by opposition from religion and other enemies, science had to avoid conjecture, had to base itself on a rigorous system of indisputable rules, in order that it could distance itself from the mythological ways of explaining the world that came before it, and defend itself. If studying the world pluralistically has led to this impasse, this dead end, can we avoid a retrenchment of the progress which science has made?
Well, yes, I think we can, because one mustn't condemn the past phases of man's development and his way of looking at the world. They were unavoidable. And in fact, even plurality has delivered colossal amounts of valuable data. What it delivers, in my view, is what I call objective content. It may not be the absolute truth, but it has aspects of truth within it, and is therefore valuable. There are phases in the development of mankind's attempts to understand reality. All of them valuable, but each one has to be superseded by a better attempt. And the things that were gained in the early attempts carried over.
So it's really a question of context. It's not saying we should throw out the data we've gathered, throw out the pluralistic methods that we've used up until this point. It's a case of realising the context in which we should use those methods, and realising the limitations of those methods when trying to formulate theories and worldviews based on them, which is something the scientists don't do at the moment. They'll take some data, get an equation out of it, and they'll base a whole worldview on that. And that's the problem, isn't it, really?
That is the problem, because it's just not good enough. Pragmatic methods are okay for use, but not okay for understanding. It's as simple as that.
Certainly the problems we've outlined here with science are huge, but not insurmountable. Can you give us examples of where you think science has been done right?
Well, the obvious example is Charles Darwin with his Origin of Species, which is a superb piece of holistic science. Another favourite of mine is Fred Hoyle's theory of the generation of energy in stars, and even their history going through phases which produced all the different elements that are in the universe. That's wonderful stuff. And then, of course, you've got whole sciences that have made colossal holistic contributions, such as geology. Without geology, we'd have had no sense of time. And then, one of my favourites is the materialist historian Michelet, French historian, who made history sing. So that there's lots of places already, and many of the soft sciences can only be holistic, they can't be deterministic.
Certainly, holism is practiced in some of the aforementioned disciplines. It's definitely not practiced in quantum physics. It's definitely not practiced in any science that relies extremely heavily on maths. Where do you see science going next in order to avoid some of the pitfalls we've been discussing?
Well, I feel that the most important job for a scientist of today is to defeat the Copenhagen interpretation of quantum theory, and I've done some work in that area already. that has to be disposed of entirely. Only then, really, will you get anyone to listen to what is needed for a modelistic science.
Many people think that the laws of nature and the universe tell us that everything breaks down. Things fall apart, energy wanes, living things grow old and die. Yes, we have some good laws which explain all that. But what about the emergence of life? What about the complexity of life? Where do they come from? Are these rare, miraculous developments? Or is this kind of complexity inevitable, following natural laws we just haven't figured out?
The gains achieved by the discoveries and inventions of science cannot be underestimated. Yet though for centuries these methods have led to great progress in dealing with reality, the very same assumptions and methods that allowed this to be possible may have also severely damaged mankind's efforts to actually understand that world, how it changes and evolves, how the entirely new can seem to emerge as if from nothing. While modern science has pragmatically and technologically been a brilliant success, false assumptions and shaky philosophical ground seems to have led to a distorted view of our reality, leaving all the biggest questions unanswered. If these problems with science are to be seriously addressed, we must constantly question our assumptions, question the consensus, question the methodologies which have led to our current worldview. For if we fail to do this, we run the risk of science becoming another failed belief system, with all its laws and dogma etched in stone.